The Fourier transform equation, we already know this particular thing. X of j omega is equals to integration minus infinity to plus infinity x of t e power minus j omega t into dt. This is what we have in Fourier transform, and inverse Fourier transform, as we already know, this x of t is equals to 1 divided by 2 into pi integral minus infinity to plus infinity x of j omega into e power plus j omega t into dt. Probably you might be having a doubts of why we are moving on to fourth module immediately, because we have still more two more topics left in this particular module 3, and problems we have to discuss. But the thing is, time is very less, and moreover, you might be having lab sessions, purely lab sessions. So for 1 week, so we will be having very less classes, very less number of classes. So rest of the modules, if you are not, at least if I am not giving any introduction also, so that will be a problem for you. So after completion of these things, we will discuss about all those things. Okay. Right. This is the Fourier transform pair. The Fourier transform exists where my uh, integral x of t into dt must be less than infinity, then only the Fourier transform exists. The existence of Fourier transform during this time only. So if it is less than infinity, then only it is exist. Otherwise, it is not. Okay. So sometimes all aperiodic signals won't be able to um, uh, stay within the limit only, within the infinity. Let us consider I have a signal e power some exponential signal, which is a periodic signal. Yes, you might be having like this. So it is like an increasing function if you are going to consider. So can you estimate? Can you estimate what is the area covered by this particular signal? So it will move to infinity. So you can't identify how much area it is going to cover. How much area it is going to cover. So this is infinity area. So understand, to estimate this sort of signals by using Fourier transform is not possible. By making use of Fourier transform, it is not possible. So such cases, we are going to use the term called Laplace transform. So Laplace transform is having the complex exponential term. So every signal will be represented with the form of complex exponential. So as we know, complex number which is going to have a combination of real part and imaginary part. It's a combination of real and imaginary. So, so the Laplace transforms are defined as the uh, Laplace transform is represents the continuous time signal in terms of complex exponential complex exponentials. So that is how we are going to use. What is the term we are going to use is the term is e power minus st. So it is able to analyze the functions or signals which are not absolutely integrable, which is which are not absolutely integrable. These transforms are used to analyze the signals or functions which are not absolutely integrable. So we have another advantage of this thing, that is Laplace transform provides broader characterization of signals when compared with Fourier transform. So these are the features which are led us to uh, Laplace transform. How we are going to write this particular Laplace transform? So the Laplace transform, if you are applying the symbol, you can identify as like this, might be like this. Laplace transform of x of t, is equals to, we can write as x of s. So with respect to s, we are writing, so that's why this is called as s domain signals or s domain representation. Integral minus infinity to plus infinity x of t into e power minus st into dt. Similarly, we can write the inverse Laplace transform, that we can write as x of t is equals to 1 divided by 2 pi j integral minus infinity to plus infinity x of s e power st into ds. This we are going to call as Fourier Laplace transform pair. Here, the S represents sigma plus j omega. So sigma will be my is the real part, or we can call that as the attenuation constant. We call this as attenuation constant, and it's coming to j omega is this imaginary part and imaginary, or you can call this as complex frequency. So you can call complex frequency here. Okay. Now, this Laplace transform has two types of Laplace transforms. We have uh, Laplace transforms exist. One is unilateral Laplace transform, and the second one is bilateral Laplace transform. So, what is meant by unilateral Laplace transform? What is meant by bilateral Laplace transform? If my signal exists only one side, either it might be 0 to infinity or minus infinity to 0. So if it is exists, let us consider only during this time. This sort of signal, if you are analyzing, then such type of things we are going to call as unilateral Laplace transform. In the equation form, we can write as x of s is equals to integral 0 to infinity x of t into e power minus st into dt. So this sort of representation from it is existing from 0 to infinity only. It is not existing from minus infinity to plus infinity. If my limit exists, if my signal is exists from minus infinity to plus infinity, then that is called as bilateral Laplace transform. Bilateral Laplace transform. Now I have a question. If I'm going to multiply x of t signal with an unit step signal, now it will become as unilateral or bilateral. How many of you saying that it will become as unilateral Laplace transform? Please raise your hands. My question is, I have a signal x of t. If my x of t signal is multiplied with u of t, unit step signal, whether now this will become which type of okay, after this I'm going to get some sort of signal. Now that signal can be applied as unilateral Laplace transform or bilateral Laplace transform. If it is a unilateral, please raise your hands. If it is a bilateral, please don't raise your hands. Right. Very good. Please down your hands. Uh, It's a unilateral because unit step function always exists from 0 to infinity, not less than 0. If my less than 0, if my value is less than 0, my time axis is less than 0, my unit step signal will be 0. So it exists only one side. So we can call this as a one-sided Laplace transform also. One-sided Laplace transform. Bilateral Laplace transform we can call as two-sided Laplace transform. Two-sided Laplace transform. Okay. Now let us consider one example. I have my signal x of t is equals to uh, e power minus at, where my t exists from 0 to, if my t is greater than 0, then only my function exists. Otherwise, this is 0. T is less than 0. Okay. Now, all of you try to solve and uh, write the result. Tell me the result. What we are going to get. Simple. It is substitution. My x of s is equals to, basically my equation is x of s is equals to minus infinity to plus infinity, and x of t into e power minus st dt. Okay. Now, what is my x of t? X of t is equals to e power minus at. It is existing between 0 to infinity. So I can rewrite this as 0 to infinity e power minus at into e power minus st dt. So I can rewrite this particular thing as in integral 0 to infinity e power minus of s plus a into t into dt into dt. So if I'm applying integration to that, I can get as 1 divided by s plus a into e power minus, yeah, we'll having minus here also. So e power minus s plus a into t over the limit 0 to infinity. So if you are going to substitute these limits here, we can get as 1 divided by s plus a into minus. So here something will be multiplied with the infinity. We will get as e power minus infinity minus e power 0 you are going to get. And I can get this as, I can rewrite this particular equation. E power infinity is 0 and minus 1 divided by minus into s plus a. So minus minus gets cancelled and I can get the equation as 1 divided by s plus. Okay. So this is my solution here. Now, sir, how to represent, how to show the graphical manner. So what is meant by graphical manner here? Why you are speaking about this particular graphical manner? So here comes with the concept called region of convergence. Region of convergence.
Excuse me, sir.
Yes, please.
So since a unit signal is defined from minus infinity to infinity,
No, no, no.
so
0
when
to infinity. Unit step signal defined from 0 to infinity, not from minus infinity to plus infinity.
minus infinity to zero, it will the value is zero, no sir.
Yes. So we are not going to
So
consider that.
then,
We are not going to consider that.
okay sir.
If minus infinity to 0, you are having 0 means why you have to consider that and why you want to solve that. There is no question of this thing, right? There is no
Okay sir.
existence. If you are multiplying with the 0 means there is no existence, then there is no point of discussing about that.
Okay sir.
Yeah. The region of convergence. So what is meant by region of convergence? The range of values that the complex variable s for which the Laplace transform exists or converges is called region of convergence. We can call as ROC, right? As ROC. Now, we have a value in the previous problem. In the previous problem, we have a solution here that is 1 divided by s plus a. Let us consider the same problem here, how to represent s plus a in ROC form. Now, let us consider I have a plane. This is S plane. So, in this, here I have j omega and here I have sigma. I have sigma. Now, if my A is greater than, sorry, if my S is, sorry, yeah. Now, what we are going to do is we are going to identify the zeros and poles here. What is meant by zero? What is meant by pole? We'll see in the next upcoming in a few minutes. What is meant by zero? What is meant by pole? Uh, so here I have a value as s plus a. This I am equating it to zero. I am equating it to 0. S plus a is equals to 0. What is my s value here? S value is minus a. If I am going to substitute my s value is equals to minus a, what happens? It will become as 1 divided by 0. You will have infinity. You will have the value as infinity, right? So less than that, this particular Laplace transform is going to exist. What happens if I'm going to represent here? This is minus a sorry, if minus a more, if minus a is, it is a more than minus a, then only it is exists. So we are going to call this as a region of s is equals to is greater than, region of s is greater than minus a. So beyond this you will have like this is, and this entire area we are going to call as ROC for this particular C. Let us consider if I'm having my signal as 1 divided by s minus a, 1 divided by s minus a. In this case, I am going to have my ROC value as, here I am going to have a, and so this is going to be my ROC for this particular signal. So here I am going to get as e power, the signal is e power 80. My signal is e power 80. Previously that is e power minus 80. This is e power 80. So I'm going to have this entire area as a region of convergence. More than this should be there. More than this should be there. Okay. Now, we have one more thing we have to discuss, that is now how to relate this particular Laplace transform with the Fourier transform. Is there any relation? This is a frequently asked question, that is, right, derive the relation between Laplace transform and Fourier transform in, previous examinations and all. You got this? So here we have relation between Laplace transform and Fourier transform. To give this, I'm considering my Laplace Fourier transform equation. So what is my Fourier transform equation? I can write as x of j omega is equals to integral minus infinity to plus infinity x of t e power minus j omega t dt. In general, this particular Laplace transform, sorry, Fourier transform exists if my value is less than infinity. What is the value? Area covered by this particular x of t must be less than infinity. Mod x of t is dt must be less than infinity. There only it is existing. Okay. Now, what is my Laplace transform? X of s is equals to integral minus infinity to plus infinity x of t e power minus st dt. So we already know one thing. What is s? My s value is equals to sigma plus j omega. If I'm substituting this here, I can rewrite this equation as integral minus infinity to plus infinity x of t e power minus sigma plus j omega into t into dt. So further I can rewrite as integral minus infinity to plus infinity x of t e power minus sigma t into e power minus j omega t dt. Now, if you observe here one thing, if my x of t signal is multiplied with the e power minus sigma t, and then if you are applying Fourier transform to that, finally you are going to get the Laplace transform equation here. If you observe the equations here in this way, this particular equation with this particular equation, so you can see that the Fourier transform or Fourier transform of x of t is multiplied with e power minus sigma t is nothing but your Laplace transform. Nothing but your Laplace transform of x of t. So further you can write as Fourier transform. In the textbooks you are able to see like this: x of t is multiplied with e power minus sigma t is equals to Laplace transform of x of t. Laplace transform of x of t. This is the relation between Laplace transform and Fourier transform. So far, any doubts?
Sir,
Mm.
in region of convergence,
Mm.
will you show that slide again?
Yeah, it is there.
Okay. Sir, if you substitute S is equal to minus 2a,
Mm.
it will not
That is
infinity,
not
sir.
not a convergence region. That is not in a convergence region. S is equals to minus
Okay.
2a will be not in a non-convergence region, non-ROC. That will be placed here at say here around, I think somewhere. If it is a minus 2a means double the time of a. So somewhere here you are going to get that. So obviously you won't find anything. So that actually won't find means that is not in a region of convergence. This point should be neglected. Any
Okay.
other questions?